Welcome. If you are joining us today, you are exactly our kind of person, a fellow curious learner who really wants to understand the foundational mechanics of the
Yeah,
universe.
the really big questions.
Exactly. So today's deep dive is an absolute classic. Stephen Hawking's legendary book, A Brief History of Time.
Such a monumental piece of work.
It really is. And our mission today is ambitious, but pretty straightforward. We are going to shortcut through centuries of mind-bending physics and astronomy.
Moving all the way from ancient myths to the edge of quantum mechanics.
Right, and we are going to do it without getting bogged down in the math, because, nobody wants to do calculus in their head right now.
Definitely not. But it's a remarkable journey to trace. We are looking at how humanity's understanding of reality has evolved, the shifts in our frameworks, and the ultimate questions that still keep theoretical physicists awake at night.
So a well-known scientist?
Often said to be Bertrand Russell, I think.
Yeah, Bertrand Russell. He is giving a public lecture on astronomy. He's explaining how the Earth orbits the sun and how the sun orbits the galactic center, the standard model.
Right.
And at the end of the lecture, an old lady at the back of the room stands up and says, "What you have told us is rubbish. The world is really a flat plate supported on the back of a giant tortoise."
A classic counter-argument.
Right. So the scientist gives the superior smile and asks, "Well, what is the tortoise standing on?" And the old lady replies, "You're very clever, young man, very clever, but it's turtles all the way down."
What's fascinating here is that while we naturally laugh at the turtle story, we have to pause and ask ourselves how we really know what we know.
Yeah, why are we so certain?
Exactly.
Yeah.
Why are we so fiercely certain of our current picture of the universe? What actually is time? Did the universe have a definitive beginning? This deep dive will explore how our obvious scientific facts today might seem as strange as a tower of turtles to future generations.
Okay, let's unpack this by going way back to 340 BC. We are talking about the Greek philosopher Aristotle and his book On the Heavens.
Right.
It is easy to assume ancient thinkers were just guessing, but Aristotle actually had three brilliant observational proofs that the Earth was a round sphere. First, he looked at lunar eclipses.
He realized that when the Earth comes directly between the sun and the moon, the shadow that Earth casts on the moon is always perfectly round.
Which is a brilliant deduction.
It really is.
Huh.
Because if the Earth were a flat disk, as many believed, that shadow would occasionally look elliptical or stretched out, depending on the angle of the sun. But a sphere will always cast a circular shadow, regardless of the orientation.
And he didn't stop there. His second proof came from travelers. Greeks traveling south noticed that the North Star appeared lower on the horizon compared to its position when viewed from regions further north.
Because the Earth curves away.
Exactly. From the North Pole, it's directly overhead, but at the equator, it sits right on the horizon. Aristotle even used these differences in the star's position to estimate the Earth's size at 400,000 stadia.
We don't know the exact modern conversion for stadia, but historians estimate his calculation was about double the actual figure. Still, deducing the curvature of the planet just by walking south and looking up is an astonishing feat of human intellect for 340 BC.
Definitely. And his third proof was simply looking out at the ocean. When a ship is approaching on the horizon, you don't see the whole ship at once.
You see the sails first.
Right, the sails first, and only later do you see the hull cresting the water.
But we have to consider the broader context of his worldview. Despite knowing the Earth was round, Aristotle firmly believed that it was completely still, and that the cosmos revolved around us.
The geocentric model.
Yes. If you picture the dusty, ancient cathedral libraries of the time, those texts heavily relied on a second-century scholar named Ptolemy. He expanded Aristotle's idea into a complete cosmological model. He placed the Earth right at the center, surrounded by 8 crystalline, spherical shells that held the moon, the sun, the stars, and the known planets.
The source notes this model was highly accurate for tracking planetary movements at the time, but it had a strange quirk. It required the moon to follow a path that sometimes brought it twice as close to Earth as at other times. You'd think that would be a red flag.
You would think so, but the model endured for centuries because the Christian church absolutely loved it.
Because it fit their narrative.
It aligned beautifully with their theology. By defining a finite system of 8 spheres, it left plenty of physical room outside that final sphere for heaven and hell. It was a mathematical model that perfectly accommodated religious doctrine.
Which explains why challenging it was so dangerous. In 1514, a Polish priest named Nicholas Copernicus proposed a radically different model where the sun was at the center.
The heliocentric model.
Yeah, but he circulated his ideas anonymously at first because he was terrified of being accused of heresy.
A very justified fear at that time. It took nearly a century for the final paradigm shift to occur. In 1609, Galileo turned his telescope toward Jupiter and observed small moons orbiting the gas giant.
Meaning everything didn't orbit Earth.
Exactly. It was revolutionary because it proved definitively that not everything in the universe orbits the Earth. And around the same time, Johannes Kepler tweaked Copernicus's sun-centered model by demonstrating that the planets move in ellipses, not perfect circles. Suddenly, the math and the observations perfectly aligned.
It's funny you mention those early orbital models because the underlying physics of why they move in ellipses doesn't actually get unified until Isaac Newton steps in.
Right, in 1687.
Yeah, he published Principia Mathematica. Now, the famous story of the apple falling on its head, the source notes that's probably just a myth. But what Newton actually did was mathematically formalize the laws of motion and universal gravitation. He proved that every object in the universe attracts every other object.
And the heavier the objects are, and the closer they are to each other, the stronger that gravitational pull is.
Right.
If we connect this to the bigger picture, Newton's brilliant discovery actually birthed a massive logical paradox. If universal gravitation dictates that everything is constantly attracting everything else, and if the universe is infinite and static, as was the prevailing belief, then eventually all those stars should attract each other and collapse into a single, incredibly dense point.
Like a giant cosmic crunch.
Exactly.
Huh.
In 1691, Newton wrote a letter grappling with this. He theorized that in an infinite universe, things might avoid collapse only if every single star was perfectly distributed and balanced against the others.
But logically, any tiny disruption in that infinite web would cause a runaway chain reaction of gravity.
And I'll see the problem.
Yeah.
An infinite universe simply cannot be static under Newton's own laws. It must be dynamically expanding or contracting.
Which leads to another huge philosophical mind-bender from 1823, courtesy of Heinrich Olbers. It's known as Olbers' paradox. He pointed out that if the universe is truly infinite and static, then no matter where you look in the night sky, your line of sight should eventually end on the surface of a star.
So the sky should never be dark.
Right. The entire night sky should be as blindingly bright as the sun. Olbers tried to solve his own paradox by suggesting that maybe vast clouds of interstellar dust were absorbing the light from those distant stars.
But the laws of thermodynamics easily debunk Olbers' dust theory. If dust were absorbing an infinite amount of starlight over an infinite amount of time, the dust itself would heat up until it glowed just as brightly as the stars.
So it wouldn't solve the problem at all.
No, it wouldn't. The only logical solution to the paradox is that the stars must have had a definitive beginning. They're far enough away that their light simply hasn't reached us yet.
And the definitive proof of that beginning arrived in 1929. Edwin Hubble, observing through the Mount Wilson telescope, discovered that distant galaxies are moving away from us. The universe isn't static, it's expanding.
Which is a staggering implication.
It really is, because if the fabric of space is expanding today, it means if you rewind the clock, everything was once consolidated into a state of infinite density and curvature. Enter the Big Bang Theory.
Right.
Here's where it gets really interesting. Before Hubble's discovery, the beginning of the universe wasn't largely considered a question for science. It was the domain of theology. For example, St. Augustine wrote The City of God, estimating the universe was created around 5000 BC. He based this timeline on tracking human progress memory of past events, the invention of tools, and so on. And archaeologists today actually track early civilization back to around 10,000 BC, so he was looking at the right kind of data, just interpreting it as the absolute beginning of everything.
That linear view is a striking contrast to how the ancient Greeks viewed the cosmos. Philosophers like Aristotle abhorred the idea of the universe having a beginning. To them, a beginning implied a creator stepping in to start the clock. They much preferred the idea of an eternal universe.
So how did they explain human progress?
They argued that occasional massive floods or natural disasters would wipe out civilization, forcing humanity to reset its technological progress without requiring a cosmic genesis.
But the concept of a definitive beginning creates massive philosophical headaches, which the philosopher Immanuel Kant called antinomies, or paradoxes, back in 1781. Kant pointed out that if the universe had a beginning, what in the world was happening in the infinite expanse of time before it started?
It's a tough question.
And conversely, if the universe had no beginning and existed forever, how did we ever reach the present moment? You can't cross an infinite stretch of time to get to now.
And here is the profound revelation of this deep dive. St. Augustine actually solved this philosophical trap centuries before Kant or modern physicists. When critics would mockingly ask Augustine what God was doing before making the universe, he argued that time itself is a property of the universe that God created. Therefore, time did not exist before the universe.
So time isn't just a backdrop that things happen in, it's part of the physical structure itself.
Exactly that. And amazingly, modern physics completely agrees with this theological intuition. At the exact moment of the Big Bang, the universe was infinitely dense, meaning all our current mathematical models and physical laws, including the dimension of time, completely break down.
Wow.
Time literally started at the Big Bang. Asking what happened before the Big Bang is fundamentally meaningless because there was no before.
That is just wild to wrap your head around. But it transitions us perfectly into understanding what science actually does when it encounters these boundaries of reality. What makes a good scientific theory?
That's the core of it.
According to the source, it must do two things: make accurate predictions about the future and be falsifiable by observation. Aristotle's old idea that everything is made of earth, air, fire, and water made zero testable predictions. Newton's theory of gravity made incredibly precise predictions that we could measure.
If you imagine shifting our view from those ancient texts to a chalkboard filled with floating mathematical equations, you can see the current, somewhat frustrative state of modern physics. We find ourselves relying on two wildly successful but fundamentally incompatible theories.
Okay.
The first is general relativity. This framework explains the macroscopic universe. It handles gravity, the orbits of planets, and the large-scale structure of spacetime, scaling all the way up to a trillion miles.
And the second partial theory is quantum mechanics, which deals with the extreme microscopic scale phenomena happening at a millionth of an inch.
Yes, but here is the glaring problem that keeps physicists up at night. These two foundational theories fundamentally contradict each other. General relativity requires spacetime to be a perfectly smooth, continuous, predictable fabric.
Right.
Quantum mechanics, on the other hand, dictates that at the subatomic level, energy and matter are quantized. They are discrete, jumpy, and governed by pure probabilistic chaos. They cannot both be entirely correct.
So what happens when you combine them?
When you try to apply both sets of math to the singularity of a black hole, or the Big Bang, the equations literally spit out infinities and break down. So the holy grail of science today is finding a way to unify them into a single quantum theory of gravity.
A single unified theory.
This raises an important question, a real paradox regarding our search for this ultimate rulebook. We operate under the assumption that we are rational beings, freely making observations to deduce this unified theory. But if a completely unified theory truly governs every particle and interaction in the universe, wouldn't that theory also completely determine our search for it?
Oh, I see. So the theory itself dictates our neurological ability to understand it. It could theoretically predetermine that we come to the wrong conclusion.
Yes, it becomes a question of rigid determinism. The source brings Charles Darwin's theory of evolution into this paradox. Natural selection suggests that organisms survive because they accurately observe their environment and adapt. Our intelligence and our scientific models have definitely aided our survival so far.
Sure.
But there is no guarantee that finding the ultimate fundamental theory of the universe will continue to confer a survival advantage. In fact, our scientific discoveries like harnessing nuclear energy also carry the potential to destroy our species entirely. We might not even need a unified theory of gravity to survive, yet humanity's innate, insatiable curiosity simply won't let us stop searching.
That curiosity is exactly what shattered our oldest, most stubborn assumptions about the nature of space and time. Let's look at how we got things wrong for so long. For centuries, people blindly believed Aristotle's assertion that heavy objects fall faster than light objects.
It seemed like common sense.
Right. They assumed the heavier the object, the stronger the downward pull, so it must fall faster. It was accepted without rigorous testing.
And that dogma held until Galileo introduced empirical testing.
Now, I always picture Galileo dropping things off the Leaning Tower of Pisa, but we need to debunk that historical myth. What he actually did was much more controlled. He rolled balls of different weights down smooth, sloped ramps.
To slow down gravity.
Exactly. By doing this, he slowed down the effect of gravity, making the acceleration measurable with the crude timing devices of his era. And he proved that weight does not affect acceleration. If you remove air resistance, a heavy ball and a light ball accelerate down the ramp at the exact same rate.
And we have a stunning modern validation of this principle. During the Apollo 15 mission, astronaut David Scott stood on the moon where there is no atmospheric drag. He dropped a falcon feather and a heavy metal hammer simultaneously.
I've seen that video.
Millions watched on television as they hit the lunar dust at the exact same instant.
It's a beautiful visual of raw physics. And Galileo's observations allowed Newton to formalize his famous laws of motion. First, objects move in a straight line at a constant speed unless a force acts on them. Second, force equals mass times acceleration. So a heavier car needs a stronger engine to speed up. And third, gravity depends on mass and distance.
But wait,
Yeah.
if gravity pulls harder on a massive object, how did Newton reconcile the fact that it doesn't plummet faster than a light object?
Oh, right.
It comes down to inertia. A heavier object has double the gravitational force dragging it down, but it also has exactly double the mass resisting that change in motion. The increased pull and the increased resistance perfectly cancel each other out, resulting in the exact same rate of acceleration.
That's incredibly elegant.
It is. But Newton's laws did something far more disruptive to human philosophy. They shattered the concept of absolute space.
How so?
Well, Aristotle thought there was a fundamental state of absolute rest in the universe. Newton's math-proved motion is purely relative. Imagine you are on a train moving 90 miles per hour in a straight line, and you bounce a ping pong ball on a table. For you inside the train, the ball goes straight up and straight down.
Right.
But to an observer standing outside on the tracks, that ball doesn't drop straight down at all. It travels in a long parabolic arc because the train is carrying it forward while it falls.
So there is no true motion. It is entirely dependent on the frame of reference of the observer.
Exactly.
And apparently, Newton hated this conclusion because it contradicted his theological view of an absolute universe governed by an absolute God. But the philosophers of the time completely embraced it.
It fundamentally changed our relationship with reality. And this transition away from absolute space naturally leads us to the mysteries of the speed of light. In 1676, a Danish astronomer named Olaus Romer made a brilliant observation.
With Jupiter, right?
Yes. He noticed that the moons of Jupiter were eclipsing at slightly different intervals. Why? Because the Earth and Jupiter are constantly moving in their orbits. When Earth was moving further away from Jupiter, the light from those eclipses took longer to cross the expanding distance to reach our telescopes.
That makes perfect sense.
Romer used this delay to prove that light does not travel instantaneously. It has a finite speed. He estimated it at 140,000 miles per second.
Which is incredibly close to the actual speed of 186,000 miles per second.
A monumental achievement for the 17th century. The final piece of this classical puzzle came from James Clerk Maxwell in 1865. He proved that light is actually an electromagnetic wave traveling at a fixed speed. He showed that different wavelengths create different phenomena. Long waves give us radio waves, shorter ones give us visible light, and even shorter ones give us X-rays.
But this brilliant discovery left a lingering, agonizing mystery for physicists.
He did.
Because under classical mechanics, every wave needs a medium to travel through, like sound waves through air or ocean waves through water.
Exactly. If light is a wave traveling at a fixed speed across the vacuum of space, what exactly is it undulating through? To solve this, scientists hypothesized a substance called the luminiferous ether that supposedly fill the entire universe.
Just to make the math work.
Pretty much. It was a necessary placeholder in classical physics, and the pursuit to measure our movement through this mysterious ether perfectly set the stage for a young patent clerk named Albert Einstein to arrive and tear up the rulebook once again.
Okay, we have covered a massive amount of ground today. From that old lady's tower of turtles to Aristotle's round earth proofs to Galileo's slope ramps, the expanding universe of the Big Bang, and the current friction between the smoothness of relativity and the chaos of quantum mechanics. So what does this all mean?
It's a lot to process.
It really is. It means that human knowledge is this incredibly dynamic, constantly evolving construct. What feels like absolute, unquestionable common sense today might just be the flat earth of tomorrow.
And that leads perfectly into a final thought I want to leave you with. Building on that Darwinian paradox of science we discussed earlier, we talked about how our evolutionary drive for survival pushes us to understand the universe.
Right.
But consider this. If the ultimate unified theory grants us absolute deterministic power over nature, much like early quantum mechanics gave us the terrifying power of the atom, does the universe purposefully keep its final secrets hidden? Perhaps the fact that we cannot easily reconcile gravity and quantum mechanics isn't just a failure of our current mathematics. Perhaps it is a natural cosmic safety mechanism, ensuring that a species only unlocks the ultimate power when it has evolved enough not to destroy itself with it.
Wow. That is definitely something to chew on. Thank you so much for joining us on this deep dive. Tonight, take a moment to look up at the night sky, look at those distant stars, and ponder just how long that light took to reach your eyes. Keep questioning, keep learning, and we will catch you